The magnetic field through a circular loop of 12 centimeter in radius and 8.5 ohm resistance changes with time as shown in figure. So we have this figure or diagram or graph, and we find in this figure time is taken along the horizontal axis and is measured in second, okay? And we have magnetic field represented by the symbol B and is measured in Tesla, and magnetic field is taken in vertical upward direction. And let's come to this, okay, question. The magnetic field is perpendicular to the plane of the loop. Calculate the induced current in the loop and plot it as a function of time. So we are asked to find the induced current, and we are asked to plot it, that is induced current, as a function of time. So let's understand this problem with reference to this diagram, okay? So I'm drawing this. Let us take positive x along this direction, positive y along this direction, positive z along this direction. And from this figure given in the question, okay, we have magnetic field acting in vertically upward direction. So let us take magnetic field along positive x-axis. Okay, so we have magnetic field acting vertically upward. Now we have a circular, or I'm taking circular loop. Okay, this is circular loop in xy plane, and from question, magnetic field is perpendicular to the plane of the loop. Okay, so we have magnetic field in plus z direction. So magnetic field is perpendicular to xy plane, that is perpendicular to the plane of the circular loop, and the radius of the circular loop is r. So r equals 12 centimeters. So we can change this into meter. Okay, so we have this. Now let n, okay, be the number of turn in the circular loop. So, or turns in the circular loop. So this equals 1. Okay, so we take number of turns or turn equals 1. So we have this. Now let us find the area of this circular loop. Okay, so let us find its area. Area of loop A equals pi r square. So let us find it. Okay, let us find this. So the area is, so I'm writing over here, the area of circular loop is 0.0452 meter square. So we have this. Okay, we have this. So we have this. Clear? Now, what we do is that, okay, we are asked to calculate the induced current in the loop. Okay, we are asked to find the induced current in the loop. So what we do to find induced current. Okay. Now, next, when we look into this question, okay, we have coil or loop having resistance. Its resistance R equals 8.5 ohm. So we have this. So this is to be noted. Okay. So we have this. Clear? So I'm erasing this also. Now, we know induced current. So let us denote it by symbol II. Okay, so I'm using this symbol. So we know induced current, this equals, okay, induced EMF, and let us denote it by symbol EI. So I'm writing in magnitude, okay. I'm taking the magnitude of induced EMF divided by resistance. So we have this. So therefore we can write induced current equals induced EMF by resistance. So in order to find, okay, so in order to find induced current, we need to find induced EMF. So how we find induced EMF now? Next. We know induced EMF EI equals, okay, so we can write in this way, minus d phi b by dt. Okay, we have this. So this represent change in magnetic flux. Okay, and this is change in time. Okay, so we have it. Now let's see. We know this, okay. We know magnetic flux phi b equals n BA, okay, this is in magnitude. So we have this. Okay, we have this. Therefore, we can write induced EMF equals minus d by dt, and magnetic flux is n BA, okay, and n is 1, okay, for this circular loop. So we can write EI, that is induced EMF, equals minus, I'm taking this area outside since it is constant, okay, area is constant, so we can write in this way, n is 1 and area is constant, okay. Therefore, induced EMF equals minus a d b by dt. So we have this, and let us call it equation 2. Now we have to generalize equation 2 for this graph or diagram. Okay, we need to understand this. So I repeat once again, we have to generalize equation 2 in order to use it for this given diagram. Okay, so we have this, okay, induced EMF equals minus a dB by dt. This is equation 2. Therefore, we can write induced EMF, okay, and this way, minus a, and we have dB by dt, or we can write it in this way, B2 minus B1, because it represent, the numerator represent change in magnetic field and the denominator represent change in time, okay, or time interval. So we have T2 minus T1. Okay, so we have this. So let us call it equation 3. Okay, we have this, and we have this graph, okay, time in second, magnetic field in Tesla, this is 0, this is 2, This is 4 and this is 6. Okay. And we have this. This is 2. Okay, we have this. Let's see. Okay, we have this. So we have this. Now, this is the graph, okay, given. This is given. This is given from question, okay, we have this. Now, let us call this region, okay, as region 1, okay. This is region 1. This is region 2 of the graph. And this is region 3 or third region of the graph. So we have this. Now, what we find, okay, from figure or graph, okay, from figure or graph. So in region 1. So for region 1, okay, we can see zero is less than t is less than 2. Okay, so we have this 2 seconds. So in region 1, we have this condition for time. Okay, so we have this. Now in this region, we need to find induced EMF, because we know induced current equals induced EMF by resistance. So in order to find induced current, okay, in region 1, or in order to find induced current for this part of the graph, okay, we need to find induced EMF. Clear? Now, what we do, using equation 3, okay, so we are going to use equation 3. What do we find? Induced EMF for first region, okay, so I'm writing in this way. This equals minus, and we know area, okay, we have calculated the area. It is 0.0452 meter square. Okay, so I'm writing area is 0.0452 meter square, and it is constant. Okay, it is constant, so we have area 0.045. okay, so 2. Clear? Now magnetic field, okay, let's see in this way. So we are taking this part. So magnetic field is varying from this point to this point. And what we find, okay, B1 is 0, okay, and B2, this point, B2 equals 1 Tesla. So B2 is 1 Tesla. So I'm writing in this way, 1 minus 0 divided by T2 minus T1. Okay, so this point gives T2 and it is 2 seconds, and this represent T1 and it is 0. Okay, so we have 2 minus 0. So we have this. So induced EMF, okay, for this part of the graph or for this region, okay, for this region or for this interval of time, let's say for this interval of time, equals minus 0.0452 divided by 2. So let's find this. So we have induced EMF equals minus 22.6 into 10 to the power minus 3 volt. Okay, we have this. So we can also write in this way. Induced EMF for this interval of time equals minus 22.6 millivolt. So we have this. Okay, so we have this. Now let us find induced current, okay, for this interval. Okay, now induced current, so this is induced current for this region 1, and this equals, okay, we are using this expression, induced EMF by resistance. And what is induced EMF? Minus 22.6. Okay, so let's write in this way, millivolt divided by, or let's write in this way, okay, 10 to the power minus 3 volt divided by, so we have a resistance of the coil, okay, it is given, and resistance of the coil is 8.5 ohm. So I'm writing over here, R is 8.5 ohm, 8.5 ohm. So let's find this, okay. So this gives us minus 2.65, okay, into 10 power minus 3 ampere. So we can write in this way, okay. We can write induced current in region 1 equals minus 2.65 milliampere. So we have this. Okay, so we need to note this, okay. So we have this. Now we go for region 2, or we go for this interval of time, okay, from 2 seconds to 4 seconds, okay. So I'm writing equation 2, minus A B2 minus B1 by T2 minus T1, okay. We have this, and R equals 8.5 ohm, and area, okay, this area is 0.0452. Area is 0.0452 meter square. Now So now we go for reason 2. Now, to find induced EMF, okay, in the interval, so let me write in this way, in the interval 2 seconds, okay, this is less than t is less than 4 seconds. So we are going to find for this interval. So this is reason 2, okay, it is reason 2 in the graph. So we find it for this reason. Okay, now we use equation 2, okay, so this was equation 2. So let's say equation 2, okay, sorry, it is equation 3. So this is equation 3. Using equation 3, induced EMF in reason 2, okay. So what we find, okay, what we find, there is no change in magnetic field. So in reason 2, there is no change in magnetic field. Therefore, what we get, okay, B2 minus B1 equals 0. So if this is 0, then induced EMF is 0. And if induced EMF is 0, then induced current, okay, for this interval of time or for reason second, okay, equals 0. Therefore, we can write induced current for reason second equals 0. So we have this. Okay, we need to note this. Now let's go for reason third. Okay, this is reason third. Okay, now I'm writing over here. To find induced EMF in the interval, okay, 4 seconds is less than t in this interval, okay, is less than 6 seconds. So this is reason third. So we have this. Okay, so we use this formula. So reason third, we can see from the graph, okay. For reason third, we have this. So let me draw in this way, okay. For reason third, we have this. This is 4, this is 6, and this is 1. So this is B1, this is 1 Tesla, and this is B2 equals 0 Tesla, okay, and T1 equals 4 seconds, and T2, okay, this equals 6 seconds. So what we do now for reason third, okay, induced EMF. So we are using, as I said earlier, using equation third, okay, we can write in this way. Minus area is 0.0452 and change in magnetic field is 0 minus 1, okay? And we have time interval, okay? 6 minus 4. So this gives us 0.0452 divided by 2. So we are getting this equals, okay? You see, we are getting induced EMF equals minus 22.6 millivolt for reason first. Okay. Now for this also, okay, we get plus 22.6 millivolt when you do the calculation. Okay. Let's see. We have minus 0.0452 by 2. And for reason third, we have plus 0.0452 divided by 2. So we get this. Okay. Now let us find induced current for reason third. Okay. So this equals 22.6 into 10 to the power minus 3 volt divided by resistance is 8.5 ohm. So again, we get the same value in magnitude as in reason 1. Okay. 2.65. Okay. So I'm writing directly. So this is 2.65 milliampere. So we have this. So we have calculated, okay, induced EMF and induced current for reason 1, reason 2, and reason 3. That is for this interval of time, for this interval of time, and for this interval of time. Now we are asked to find, okay, or we are asked to plot the graph, okay, between induced current and time. So how we do it? Okay, let's say it. Plot induced current as a function of time. So I'm writing all the values, okay, we have calculated. This is minus 22.6, okay, minus 22.6 millivolt, and induced current is minus 2.65 milliampere, minus 2.65 milliampere. Next, for reason second, okay, induced EMF is 0 and induced current is also 0. And for reason third, okay, we have 22.6 millivolt. Okay, this is positive, and induced current is 2.65 milliampere. So we have this. Okay, this is calculated. So we have this. So I'm drawing the graph, okay, given in the figure. So we have this. We have time in second and magnetic field in Tesla. So this is given from question. Okay. Now we need to plot induced current as a function of time. Okay. So we have this. We have induced current. Okay. And we have calculated induced current in milliampere. Okay. So I'm writing in this way, milliampere. So we have this. This is in milliampere. So we have this. So this is 0, okay, or origin. So we have this. Now, as I said earlier, this is reason first, reason second, and this is reason third. Now, what we find for reason first, okay, induced current is negative, okay, minus 2.65 milliampere. So for this interval 0 to 2 seconds, okay, for this interval, this is 2. Induced current is negative and it has value minus 2.65, okay. So it has this value. And for 0 to 2 seconds, we have induced current, okay, minus 2.65 milliampere. So we have this, okay. So let me use this ink, okay. So we have this. Now for reason second, that is for time interval between 2 seconds and 4 seconds, induced current, okay, is 0. Okay. So induced current is 0. So induced current is 0. Okay. Induced current is 0. Okay. There is no induced current for this interval of time. That is for 2 seconds to 4 seconds, induced current is 0. Now next, okay, for reason third, let's see for reason third, it is positive, okay, this is positive 2.65 milliampere. So for this interval of time, okay, that is for 4 seconds to 6 seconds, we have induced current which is plus 2.65 milliampere. So we have this, okay. We have this, okay. So this is the plot, okay. It is the plot of induced current as a function of time.